everyone. I am so excited to be here today. This is my first lunch break science as a presenter. Today, I'm going to present roughly 45 minutes of astronomy content to an audience I cannot see. So it's not too dissimilar from my day job in the dome. Although you can see me, I suppose, so I should be careful with how much I'm gesticulating. And we're not under a quarter-acre planetarium screen. So small differences, I think, will be able to make it work. My name, as you can see, is Mariarosa Marinelli. My pronouns are she, her, and hers. And today I will be leading y'all into the wonderful and weird world of post-Starburst galaxies, which serve as glimpses of galactic transformation. And actually, I forgot, I'm going to go ahead and turn captions on. These are automated captions from Google Slides. So they might not be perfect, but hopefully if there is anyone who needs captions or if captions are useful, then that might be a little bit helpful during my presentation. So Jim gave me a wonderful intro, so I'll just give you a little bit more about me before we get started. I have been working in the dome as an astronomer, delivering shows for about 3 years, if we don't count the furlough time. And I've actually been at the museum since mid-2016. So I want to take a moment and express my gratitude for the opportunities that the folks at the museum have extended to me to learn and grow over the years. It's a really awesome place with some really awesome people, not just me. And I especially want to thank Jim for letting me take over and sort of ramble about my very niche research topic. I have a bachelor's degree in physics and mathematics from VCU. So I think I'm contractually obligated to say go Rams. And in 2017, I spent a truly transformative summer in New York City at the American Museum of Natural History. It was a National Science Foundation internship under the direction of Dr. Charles Liu, who is, and I hope he's in the, he's watching right now, so I hope I get all of his titles right. He's an associate in astrophysics at the Hayden Planetarium and the AMNH, as well as an associate professor of astrophysics and director of the Verrazano School at College of Staten Island, CUNY. Great guy, wonderful guy. After my internship ended, we remained collaborators along with several other students and researchers around the globe. So the work I'm going to be talking about today really encapsulates about 3 years of collaborative research I've been a part of. And I love that about science and astronomy, especially in these days that we're able to stay connected and make really cool progress through science together. I've been to a fair number of scientific conferences. I've sat in a lot of science lectures, and in the context of being a science communicator and educator, I think it's important that I don't assume that everyone has the same foundational subject knowledge that I take for granted. So I'm going to start my talk today discussing broadly what galaxies are. Once we have a handle on that, we'll dive into how they change and evolve over time. Now, there's a particular category of galaxies I'm really interested in. So I'm going to explain what post-Starburst galaxies are and sort of make the case for why they're important. And after that, we'll delve sort of into my research, which uses a very particular observation technique and set of technology to better understand those types of galaxies. So we'll end up discussing how I've used IFU spectroscopy to understand post-Starburst galaxies better, but I don't want to throw a whole lot of jargon out there, especially if a lot of this is very new to some people watching. So we start at the beginning, not at the very, very beginning. We're not going to go all the way back to the Big Bang, but it is worth talking about what galaxies are in the first place. So if you have a moderate amount of astronomy knowledge already, this question might seem kind of silly, but it's actually one that humans have struggled with even asking for thousands of years. We get the word galaxy from the Greek word meaning milky, and I tried to practice how to say this, and I think my Greek is just not up to par, so I won't butcher it. But we get the word galaxy from the word that the ancient Greeks used to describe the stripe across the sky, which is our view within our own galaxy of our Milky Way. And the background image here is a really amazing map of our galaxy that was taken by the Gaia collaboration. Now, we used to think that our Milky Way was all there was until the combined work of Edwin Hubble, pictured on the bottom left, and Henrietta Swan-Leavitt, which is top right or top left, illuminated our understanding of cosmic distances in what was then known as the Great Andromeda Nebula. So by 1924 or so, there was this realization amongst astronomers that there were things beyond the veil of our Milky Way, which in a way really kicked open a door for a new era of astronomy. our Milky Way was not the end all be all. So it hasn't even been a century since we figured out that our Milky Way is not the entire universe that's out there. There's more stuff out there, trillions of galaxies in our observable universe. But again, we have to ask, what is a galaxy? I'll make the logical assumption that if you're like watching right now, that you're a person. So you are your own entity, but you are also an entire ecosystem, your own microbiome. You are a host to trillions of microorganisms. And I'm not a biologist, but I really like comparing people to galaxies because we now know that fuzzy little patches in the sky that we thought were just nebulae in our Milky Way are actually galaxies. It's really easy to think about galaxies, especially really far away, as just astronomical objects, like little specks of light. But in reality, they're entire ecosystems made of stars, gas, dust, dark matter. We're not really going to get into that today. Black holes, planets, people, pocket length, all of this stuff. So just as humans aren't static, we're always growing and changing, so are galaxies, because they're made out of all of these component things and can undergo changes throughout their history. So when we're looking out, especially to the really far away galaxies that sometimes just look like little specks of light, in actuality, in that tiny infinitesimal splotch, there could be trillions of stars and supermassive black holes and maybe people pointing telescopes right back at us. But that's really overwhelming. So we're going to start in a more logical place. We sort galaxies according to how they look, which is called visual morphology. When it comes to people, you're not supposed to judge a book by its cover, but that's not really the case with galaxies. So this is where like the metaphor breaks down. Visually inspecting a galaxy can give you an incredible amount of information. So this is a photo of two galaxies that were observed by the Hubble Space Telescope. These aren't edited together or photoshopped or anything like that. The one that's in like the center of the image is a little bit in front of the one in the corner. And oftentimes we can see background galaxies through galaxies that are much closer to us. But in this case, we actually do have evidence that these galaxies are very close to each other in space. So the one in the center is a little bit closer to us, but not incredibly far. They are like hanging out together, like as a pair. These galaxies' names are not super important. They're just catalog names. But what we can kind of figure out just by looking at these galaxies is that they have some very visually distinct differences. NG4647 looks kind of blue. It's kind of got a spiral structure to it, but M60, which is in the center, it kind of just looks like a big blob, and it's kind of yellowish, golden a bit, little red. NGC4647 is actually about the same size as the Milky Way. So even with M60 being closer to us and skewing some perspective, it's also bigger than NGC4647. So there's a difference in the shape of these galaxies. There's differences in the size, and there's also differences in the color. And all of these differences are physically important, like to the physics of what's going on here, and are at the heart of galaxy classification. So when we classify galaxies, generally they can be divided into three groups. First, we have spirals, like our Milky Way. Others are ellipticals, so they've got this oval or spheroidal shape. And some have irregular shapes or even maybe look lens-like. And there's a color difference that generally remains constant across these categories. You have spiral and irregular galaxies that tend to be blue, and ellipticals tend to be red. And that's because star formation is happening a lot in spiral and irregular galaxies, and young hot stars that are produced when you have a whole lot of star formation are blue. So you get these blue and new galaxies, and it's very convenient that they rhyme in English. Many elliptical galaxies aren't forming stars anymore, so all of their blue and young stars have died off, and they're left with older, redder stars. So we call those galaxies kind of red and dead. And it's not always true, and we'll get to that in a minute, but these are sort of little memory devices to help you remember why these galaxies have different colors. And so the alignment of these colors and the shapes is not always constant, but it's a pretty good sort of guiding principle as we're looking at classifying galaxies. Now, galaxy classification really began with Hubble and his tuning fork. By 1926, it was apparent that galaxies could be grouped by their physical shape into different categories, and Hubble began to see links between the groups. And this diagram, this is important, this diagram suggests that galaxies change shape from elliptical to spiral, either with a bar, as you can see, sort of going down, or without a bar. And that's not actually the case. Light travels super fast, but it does travel at a finite speed. So as we look farther away from our place in the universe, we're also looking back in time, since those photons have to travel so far for so long to reach our telescopes. And as our instruments and observations improved, we began to see that the farthest galaxies from us, the galaxies from the earliest era of the universe, are predominantly spirals and irregulars. They're not all ellipticals, and that's not what we would expect if spirals were the end product of galaxy evolution. So the tuning fork is actually kind of backwards. Spirals generally evolve into ellipticals, and this sort of makes sense from a physics standpoint too. So here on the right, we have order and structure in these spiral arms and these barred features. And over time, that gives way to a galaxy without clear structure, with stars on slow or even scrambled orbits. So we go from order to disorder, which physically is a little bit more favorable than going from disorder to order. So this brings up a really important question, right? How do galaxies change? And they do in a variety of ways. But one of the most predominant ways that galaxies change is through mergers. So I have a little simulation that's going on the screen right now. Galaxy mergers happen often, and they're one of the primary ways that galaxies change over time, by interacting with other galaxies. Galaxies have an incredible amount of mass. They're bound together because of gravity, and over time, they begin to get drawn in by other galaxies' gravitational pull. They begin to dance. In about 4.5 billion years, that's billion with a B, so don't worry about it, the Andromeda and the Milky Way galaxies will begin to collide, and we're actually simulating right now what that's going to look like. In the background, you can see a really small galaxy. That's actually the Triangulum galaxy, which is nearby, but not expected to really get involved in this round of dancing. When people talk about galaxy mergers, you might hear of words like collisions or train wrecks or galactic cannibalism, which feels a little unnecessarily violent to me. For one thing, these interactions or mergers are happening on really long timescales, sometimes lasting for billions of years. And it's actually relatively rare that individual stars are going to crash against each other during these mergers. Instead, hydrogen gas clouds are going to mix together from both galaxies, and you're going to end up with new stars forming. And once the hydrogen gas is all used up, the composite galaxy can't form new stars. And as we just saw, the galaxy sort of ends up red and dead. The young, hot blue stars die off, and we're just left with those golden red older stars. And this is what we call the quenching of a galaxy. When a galaxy cannot form any more stars, has stopped forming stars, we call that quenched. And we're talking really simultaneously about two changes, right? A change in shape, in morphology, from a spiral to an elliptical, and a change in color or age of stars from blue to red. And that's important. We'll get to that in a moment. Galaxy mergers are super common. In fact, astronomers keep finding evidence of fossil galaxies in the Milky Way. So clumps of, well, let's see if I can get to the correct, here we go. So astronomers keep finding evidence for fossil galaxies in the Milky Way from the Milky Way sort of incorporating dwarf galaxies over billions of years. So we actually have two images here from a recent discovery in the last couple of years of the Gaia Enceladus dwarf galaxy, which had merged with the Milky Way. It says 10 billion years. There's sort of some discussion whether it was it's in the realm of 8 to 11 billion years ago. But it was a dwarf galaxy, a very small galaxy that had been sort of orbiting around the Milky Way and had been sort of pulled into the Milky Way and contributed globular clusters of old stars, as well as stars, gas, and dark matter, all totaling up to be about 50 billion times the mass of our sun. So we gained mass as a galaxy, the Milky Way. We gained mass by sort of folding in that Gaia Enceladus dwarf galaxy. So that's one really common way that galaxies can change shape or add mass over time. Interactions don't have to happen incredibly directly. There's a phenomenon known as ram pressure stripping. So in dense environments like clusters, where you have a lot of galaxies that are embedded in the same sort of area, the same dark matter halo, if you want to get technical, they're really close together. You get hot gas within the cluster that's known as the intra-cluster medium, and it acts like wind, and it strips away the hydrogen gas that you need to make new stars. This is known as ram pressure stripping. So this galaxy right here is called NGC 4402. And it's actually falling into the Virgo galaxy cluster, and which is causing the disk of the galaxy to actually warp. So you see this sometimes. This is one of the ways that galaxies can stop forming stars. They can start to change their shape. They can start to change the behavior, the environment that's going on within the galaxy because of the external environment that they're either moving into or they're surrounded by. Now, as the amount of hydrogen gas in a galaxy decreases, galaxies stop forming stars, right? That makes sense. If you don't have any more fuel for stars, you can't make more stars. Generally, the color of the galaxy is going to change because of that. You start off with blue when you're forming stars, you end up with red when you stop forming stars. And generally we see that ellipticals are red and most spirals are blue, but that's not universally true. We have found, and I would be remiss not to share this with you, that there are some blue elliptical galaxies out there and there are some red spiral galaxies. And to form spiral galaxies in particular, you can have a star-forming spiral just run out of gas, run out of fuel, and just start to die off. Those young stars start to die off, and you're just left with those red stars remaining in a spiral shape, which you can see in the bottom right corner on the screen. And this is actually work done by the wonderful, incomparable Karen Masters, as well as the Galaxy Zoo collaboration, looking at and trying to understand the morphologies of different galaxies that we can observe. And so with this, these galaxies aren't necessarily morphologically disturbed in order to change from a star-forming galaxy to a non-star-forming galaxy. It's not super common, but it's definitely possible. At the center of most galaxies is a supermassive black hole. And when it's actively accreting new matter around it, we call it an active galactic nucleus, or an AGN. Within a galaxy, the interstellar medium, all of the stuff inside the galaxy, can be affected by winds, jets, and radiation from that active galactic nucleus. So cold hydrogen gas that would otherwise end up as fuel to make new stars can get heated or even ejected out of the galaxy, which can slow down or stop star formation. So active galactic nuclei can actually stop the star formation in a galaxy. And this image right here, which I really love, is a multi-wavelength image of Centaurus A, which combines X-ray data, which I believe is the blue in the image, from the Chandra X-ray Observatory. There's microwave data and visible images as well. The microwave is in orange. And so this is showing you the structure of these jets from the center of this black hole that's the center of this galaxy. So they can be quite extensive. This is kind of a really extreme example of an AGN, but AGNs do come up a lot when we're talking about how galaxies are changing over time. So this all leads to sort of the title of my talk, right, was about post-starburst galaxies in particular. So starburst didn't really come up on that list necessarily, but what are post-starburst galaxies, and really, why do we care? And I care very much. And I hope maybe after my talk, then some of you will care as well, what post-starburst galaxies are. Post-starburst galaxies are a type of transitional galaxy. And so in order to talk about transition galaxies, I need to talk about the Green Valley for just a moment. This is a cartoon of a color mass diagram. I felt like it was probably the easiest sort of way to visually understand this phenomenon without having to like delve into like real data and like color indices and that sort of thing. So here we're comparing galaxies, which are the different points on the graph, according to their mass, which is correlating with brightness, and that is on the x-axis, and their star formation rate, which correlates with color, and that is on the y-axis. And we can actually identify different populations when we plot out galaxies we observe. Like pick a patch of the sky, observe it, figure out how massive those galaxies are, and figure out how fast they're forming stars, or how many stars they're forming per like 100 years or whatever. You can plot all those galaxies out, and generally you'll start to see these populations emerge. So we'll have starburst galaxies where star formation rates are really, really high. So they are forming a whole lot of stars right now, like just it's booming. Then you also have a main sequence of blue star-forming galaxies. So that's what that sort of blue population along that line is representing. And then down here, we've got a population of red galaxies, generally ellipticals, that have very low rates or are not forming stars anymore. The vast majority of galaxies will fall in really the main sequence of blue star formation, or the sort of red cloud of quenched galaxies, but also starburst galaxies, while rare, are not as rare as transitional galaxies. So this transition zone between our red population and our blue population is colloquially known as the Green Valley. And that might seem kind of funny because like blue and red together make purple, but this has to do with the actual spectral colors and the photometry that we're seeing. So when we look at like a spectrum, red on one side, blue on the other, and in between you're going to see green, basically. That's where the name for Green Valley comes from. When we look around the universe, we don't find a lot of Green Valley galaxies. So this tells us that if this is a zone of transition, right, because galaxies are not static, they're going to change over time, they're going to evolve, then this transition zone between your red galaxies that are not forming stars and those blue galaxies that are forming stars, that transition is going to be pretty fast if we're not finding a lot of galaxies out there that are occupying that part of this graph. Now, research has shown that the Green Valley is home to lots of different types of galaxies with a lot of different histories. As we saw, some blue spirals can just like run out of gas and then eventually turn red as their bright young stars die off. And in fact, red quenched galaxies could accumulate a smaller galaxy that has a lot of cold gas and sort of jump back into production, so to speak, and start forming new stars. So it's definitely not a one-way zone necessarily. You don't always go just from blue to red, though that is the trend. But there are lots of pathways through the Green Valley. So post-Starburst galaxies represent one track, one path through that Green Valley. So we'll break it down real quick. The term post-Starburst galaxies, starburst means, and I said it before, but you're forming stars at really high rates. So that's a starburst phase, when a galaxy is like just, nonstop all day and night, new stars constantly. Post means that there was a rapid shutdown of star formation. Now, it's totally possible that you can have a period where you're forming a lot of stars and eventually you slowly run out of gas, you peter off. And that's not really going to induce the same phase as a post-starburst galaxy that we're going to be looking at today. So it's a lot of star formation followed by a rapid truncation of star formation is what we're looking for here with post-starburst galaxies. Now, post-starburst galaxies are caught in the act, so to speak, because again, you're not going to find a lot of Green Valley galaxies, or you're not going to find a lot of galaxies in transition in the first place, but also the phase itself, a post-starburst phase, or really specifically what we call an E+A type galaxy, is not going to exist for very long. Post-starburst galaxies and E+A galaxies are, the name E+A is coming from the fact that we have an elliptical type stellar population. So we've got stars in the galaxy that seem like they should just be in an elliptical galaxy. You look at the galaxy, you're like, kind of looks like an elliptical galaxy. You don't have tons of star formation. This thing is quenched. It's not forming new stars. But the A in the E+A comes from the fact that the brightest, most luminous stars that are contributing to the galaxy's spectrum, fingerprints, so to speak, are A-type stars. And A-type stars have a very specific lifespan. So if there was an incredible amount of star formation in a very short period of time, a starburst phase, and then the starburst stops, star formation stops, your O-type stars, which are the spectrum that's on the bottom on the left, so that purple spectrum, and your B-type stars, which are that blue spectrum, those stars are going to die off. They don't live very long. Those are the O and B-type stars that die off once you stop forming star formation. About 1 billion years out from a starburst ending, what you're going to have is a large population of A-type stars. Those are the brightest stars left over from that starburst phase. And So when we look at the spectrum of an E plus A type galaxy, what we see is an elliptical stellar population that kind of looks like an A-type star's spectrum has been just slapped right on top of it, averaged out. So it's a sort of bizarre little spectrum, and that's what you can see on the right. So that's a galaxy spectrum on the right, and on the left we have just different types of stellar spectrum that are stacked, so you can see them individually. This phase is not going to last very long. Once those A-type stars start dying out, all the light that you're going to get from that galaxy's spectrum is going to be contributed much more from like K-type stars and other redder stars. So it's going to start looking way more like an elliptical galaxy spectrum rather than this post-starburst phase. So it's a rare phase in and of itself. We think only about 1% of galaxies in the known universe are going to be sort of in this phase. And because they represent a transitional phase, they can give us unique insight into how galaxies evolve. So do they come from major mergers? Why do they quench? How do they quench? Why did they have a starburst phase in the first place? Are they more common in groups of galaxies or in isolation? And by studying post-starburst galaxies and starting to puzzle out these answers, we begin to better understand galaxies and galaxy evolution as a whole. So we're looking at a very small part of the puzzle, but that small part of the puzzle might help click other pieces into place. So I just like to say all that because I know that these galaxies are not necessarily like the really beautiful, gorgeous Hubble spirals that you see, but they're really, really important in and of themselves. So what have I been doing about this? When I joined Dr. Liu in 2017, we began by sifting through single slit spectra from the SDSS, the Sloan Digital Sky Survey, to find galaxies that looked like they might be in a post-starburst phase. So you saw on the last slide what that E plus A spectrum kind of looks like. And sort of out of context, it's perhaps a little hard to see why this jumps out so clearly. But I'll bring up a couple more spectra just to show you in comparison. These are 3 different single slit spectra from the Sloan Digital Sky Survey. And I and several other students spent several weeks in 2017 sifting through thousands of spectra until we found a few dozen post-starburst candidates. And we did this all by eye. We did this qualitatively, which was a lot of fun, and is sort of the first phase of working with Dr. Liu is getting to hunt through and look at all of these spectra yourself. And what you find is you start to understand that the shape of this spectra tells you really important information about the galaxy and the galaxy's history. So in the center, we have a post-starburst galaxy candidate. And on the left, what we actually have is an elliptical galaxy population. So this is an elliptical galaxy. It's a red and dead galaxy. It is not forming stars anymore. You have an aging stellar population. Really, if we jump back, looking at that one on the left, we get it in our head, and we jump back to these pictures of these spectra from stars. You can see that if you have a lot of like K-type stars, if you have a lot of like M-type stars, you're going to start to get a stellar population that looks a lot closer to this one on the left, where as you are getting redder, because we've got wavelengths on the x-axis, as you get redder, you have an increase in flux. These stars are a lot more red than blue, so that makes sense. As we're looking at redder wavelengths, longer wavelengths, the flux increases, and it just sort of stays stable. It flattens out. Sometimes you get some weird emission lines from AGN and that sort of thing. On the right, we have a galaxy that's actively forming stars. So this is where we're having a galaxy that has a whole lot of O-type stars, a whole lot of B-type stars, and active star formation. It looks wildly different from the other two. Sometimes it can be difficult to puzzle out the difference between an elliptical galaxy and a post-starburst galaxy. There is sort of definitely a judgment call in what we call candidates and what we don't, but once you see star formation, you're like, that's not what we're looking for, because this is a post-starburst galaxy. Got to be quenched. That's our criteria, although definitions are a little tricky in astronomy, and some research groups do include some galaxies that have residual star formation. And that can tell them different things about their populations that they are studying. But the key thing These spectra are single fiber spectra. They are only looking at the center, a small area at the center of the galaxy, which means you don't have any spatial information. You're only looking at the center of the galaxy, and that's not necessarily what you want. Like, you might want to figure out, is this galaxy doing the same thing throughout the entire galaxy? Is it quenched everywhere? Is it post-starburst everywhere? Is it forming stars everywhere? And so this is where MaNGA comes in, and it's not the Japanese comics. This is actually mapping nearby galaxies at Apache Point Observatory. If you did not know, astronomers really, really love acronyms, and especially acronyms that make it really hard when you're trying to remember like a specific tech issue, and you're like, oh, I can't remember the publication date for that paper on the fiber. So you type in MaNGA publication fiber, and you do not get what you're looking for at all. You have to add the Sloan Digital Sky Survey part to it, because you'll just get lots and lots of, and that might be fun for another time, for after you're done researching. But for now, we're going to focus on mapping nearby galaxies at Apache Point Observatory, which is MaNGA. Now, nearby, before we go too farther, nearby is a very relative term in astronomy. Here, nearby means like within about 400 million light years or so. It's around Z redshift equals 0.03. And so some of the galaxies are a little closer, some of the galaxies a little bit farther away, but that's roughly what we're talking about, 400 million light years away. So really far away from me. In terms of how far away things can be in the universe, very, very nearby. Now, MaNGA uses IFU spectroscopy, integral field spectroscopy, and this results in spatially resolved spectral maps. And the goal, which I think they finished their observations, the goal was to have about 10,000 galaxies observed in the nearby universe with these instruments. And I believe they finished their observations, though not all of the observations have been released. Like they've not all been processed through the processing pipeline and been released for science purposes. When I started working with MaNGA data 3 years ago, there were only about 2,600 galaxies that were released at the time. So as time has gone on, we've gotten more data, and sometimes the way that they process the data changes. We have to kind of go back and reevaluate what we're doing and which galaxies we're looking at and what methods of analysis we're using. So it's really fun to be working on an ongoing survey, because things are constantly changing. Now, what you see on the screen right now, on the left, we have a fiber bundle. So this is 127 fibers packed together. And these fibers are packed together in these hexagon ferrules, so that they are in these bundles. And then these fibers enable us to plug it into this spectrograph and be able to get spectra at points all throughout the face of the galaxy, which is what the image on the right is sort of demonstrating. So this correlates to what you would see if you use this 127 fiber MaNGA bundle to look at this galaxy on the right. That's kind of what you would see. And they dither the instruments as well. So they tilt them up a little bit, they wobble them around so that we get more than just the number of fibers that we are using. And we actually get really amazing spatially resolved maps of what's going on in the galaxy. So these are just some examples that were provided by the MaNGA team. So this is an example of a galaxy that was observed with MaNGA. So from left to right, we have a stellar velocity field. So that's showing the movement of stars in the galaxy. And so you can see there are a lot more than just 127 points. You have all of these little pixels, almost looks like a cross stitch pattern is where my mind goes. And this is what we actually call these spaxels, these space pixels. So that's where we're getting this data from when we're looking at the whole face of the galaxy. In the center, we have a map showing emission of hydrogen alpha. And on the right, we have the actual velocity field of the gas in the galaxy. So we can look and see, are there differences in how like the motions of the stars versus the motions of the gas in the galaxy. So it makes it a really, really powerful tool for deeper understanding. So it's pretty neat, really amazing instruments that we're using and techniques that we're using to understand galaxies in better detail. So let's dig a little deeper. This is a galaxy about 300 million light years away from Earth. It is my favorite galaxy. I have circled in white the area that the SDSS single fiber spectrum covers. And outlined in pink or like magenta is the footprint of the, in this case, it's a 91 fiber MaNGA fiber bundle. So we're gonna have 91 fibers looking at this thing, and we're gonna sort of compare the information we can get from a single fiber spectrum just pointed right at the center versus the information we can get from the MaNGA data, which I'm just gonna spoil it for you, is I think a little cooler. And that's why we do this stuff. This is why we create new ways to observe, is to better understand the universe. So just to sort of recap, that circle that I've outlined is 2.5 arc second diameter single fiber spectrum image. Like that's what we're looking at. We had pointed our telescope right at the center of the galaxy, and we took that spectrum. That spectrum is the accumulated, the summed light of all of the stars and gas and everything that we can see in that little circle. All of that is just basically averaged out. Whatever's screaming the loudest is what we're going to get, and that's the spectrum that we see. When we look at MaNGA, though, we start to see a very different picture. So first, I'm going to show you, this is the stellar velocity of this galaxy. So right away, we can see the center of the galaxy doesn't really seem to be moving with respect to the observer. In this map right here, blue is showing us the parts of the galaxy, the stars that are moving towards the observer, and red represents stars that are moving away from the observer. So what we see here is coherent rotation. This galaxy is rotating, and it's rotating sort of all together, at least all the stars are. And this stellar velocity is we also call that like the kinematics of the galaxy. A lot of elliptical galaxies that we look at have really disorganized rotation, especially if they've experienced a major merger. So seeing coherent rotation in this map is something that we would not have known if we were just looking at the single fiber spectrum. So this is one way already that, you know, we're really shaking things up with MaNGA here. So next, we're going to map out something that we call the DN4000, which is a measurement that we're taking of each spectrum. And it can be used as a proxy for the relative ages of stars. So smaller values here are going to indicate younger stars. We can see here pretty clearly, right in the center, there's like a bulge of much younger stars than the surrounding areas. And this tells us, knowing that this galaxy exhibits a spectrum that is characteristic of a post-starburst galaxy, this tells us right away that that starburst that happened seemed to have been relegated to the center area of the galaxy. So the starburst was not happening all the way through the face of the galaxy, because the disk of the galaxy, the stars around that bulge, are much older, billions of years older. So this galaxy was either already quenched or in the process of quenching when that starburst happened. That's a pretty important insight that we wouldn't necessarily know, because, well, that circle right there sort of lines up exactly where that bulge is. So, you know, we would not have known that spectrum would not necessarily be the same everywhere through the galaxy if we were just looking at the single fiber spectrum. And I really hope, I'm not trying to like trash SDSS. We do the best with the technology we have, and then we learn more and we find out better ways or more interesting ways to continue to explore the universe. And then we implement those, and then we get to compare them to the past. So finally, this is a special map that I really love a lot. This is a map that shows us the dominant ionization source. So we take measurements of each spectrum of different spectral features, and then we compare those measurements to each other. We take their ratios, we measure how large they are, and they can then get sorted depending on what those ratios look like into different classic sort of ionization patterns. So if this galaxy had residual star formation, maybe had some star formation happening in the outskirts, then what we would have seen is spaxels highlighted in purple. If at the center of the galaxy there was a really strong active galactic nucleus that was still accreting matter and screaming and really showing off, we would have seen that. It would have been magenta or this sort of darkish orange color. But what we see throughout the face of the galaxy are categories that are identified as passive and retired galaxies. And this tells us that this galaxy is right now exhibiting ionization consistent with a lot of stars that are just sort of aging. They're older stars, they're hot, they're low mass. So this tells us that there's not necessarily an active galactic nucleus that's on and running and accreting matter and sending jets out into space right now. But it doesn't mean it didn't have one in the past. And in fact, this galaxy was determined based on the difference in the rotation of the stars and the rotation of the gas in the galaxy. It was determined to actually have in the past an AGN that we believe led to the quenching of the galaxy. And that I'll mention that a little bit more in a moment. So I know I'm running a little bit low on time. We've done a lot of work in 3 years, and to go through all of it would be sort of exhausting and in some points contradicting, because as we get more data and as we are studying it and applying new forms of analysis, we start to stumble towards a closer approximation of ultimate scientific truth. So I'll just sort of sum up some of the major findings we've had so far. Our research group's samples of post-Starburst galaxies have evolved as more data has been released. So not like the galaxies themselves, but like our samples, like the galaxies we're actually looking at and identifying and calling post-Starburst galaxies or galaxy candidates have changed. So a lot of times that does lead to a better understanding of what sort of phase we're actually looking at, as you start to see samples of galaxies and you're comparing their spectra and you're comparing their features and you're saying, actually, I think we're getting away from our definition a little bit. We're getting away from this classification. Some of these galaxies are maybe a little bit farther out from a post-Starburst phase than others, and maybe that represents, something new and interesting we should explore. Major mergers don't seem to be driving quenching of these post-Starburst galaxies, even in cluster environments, just based on galaxy kinematics. And this has been pretty regular as we've looked at different samples over the years in cluster environments, out of cluster environments, that generally at least half or sometimes even more than half of those galaxies are exhibiting sort of this coherent rotation pattern. So that's pretty interesting, because for a long time, we thought that E+A galaxy phases were really driven by major mergers. And now it's looking like there are a lot of ways that you can get to an E+A phase and a post-Starburst phase. Cluster environments do tend to have a larger share of post-Starburst and E+A galaxy candidates, which seems to be in line with the literature, which is pretty reassuring, sort of reality check. And sort of as I mentioned, that last galaxy is indeed the first. A lot of descriptors here. The first dwarf elliptical post-Starburst galaxy that was discovered to have evidence for AGN feedback. And this was published in a paper led by Samantha Penny, but I was also on it, which I just like to mention. And then I also published a research note about it this year. And we believe that galaxy was sort of leaving an E+A phase. So it's got 1 foot out of the door, the galaxy we just looked at. It doesn't have an active galactic nucleus really anymore, but we believe in the past it did, and that the matter that accreted, enough matter had accreted on the galaxy, enough matter was getting, enough cold gas was getting sort of funneled out of the galaxy, that star formation turned off for the galaxy, and then the stars begin to age, and those O and B stars die off, and we get this post-Starburst phase. So we're coming in right at the end of that phase right now with our observations, but that is sort of where we determined this galaxy was sitting. And so understanding these sort of weird galaxies that are, not very typical. They're not really falling clearly into certain categories that we generally use for galaxy classification. Can be really, really useful in puzzling out how galaxies even change over billions of years. So with that, I think I can take questions. I said 15 minutes, but it looks like it's going to be about 13. But thank you all for listening to me talk. This has been a lot of fun. I'll take your questions.
Okay, we've got a few questions in the chat for you. So are most irregulars baby galaxies, or are most irregular galaxies combinations, mergers of multiple galaxies?
That is a really great question. From my understanding, most irregular galaxies tend to be sort of, it looks like they're early on in sort of their evolution, but I also have not really studied irregular galaxies in depth, and I don't want to mislead you. But that is, from my understanding, generally yes. And Charles is giving me a thumbs up, which is encouraging. So because he has a PhD in astronomy. So.
All right. So how frequently do you find spiral galaxies that are red and elliptical galaxies that are blue? How common is that?
Ooh, another great question. It's not super common, although one of our post-Starburst galaxies, I wish I had a picture sort of easily available. One of our post-Starburst galaxy candidates was identified to be sort of this like golden spiral. It looks like just like an S in space, which is amazing. So definitely not very common. And sort of that paper that Dr. Masters and her team led was sort of, I would call it groundbreaking, but groundbreaking in sort of the revelation that these galaxies are out there, and they are still rare, but not like impossible.
All right, and we've got a question here. Besides our own Milky Way galaxy, what is your favorite galaxy?
I really love, this is, I wish I'd come up with a better name for it, but I've just been calling this galaxy 311 for about 3 years now. 311 is one of my favorite galaxies just because I think in exploring it brought me on so many twists and turns. And so I feel like I really know it like deep in my heart. But in terms of sort of really cool galaxies that one's pretty cool, but I really love the Andromeda Galaxy a lot. And I think it's really fascinating that we can observe it to the degree that we can now, and even see that it is moving through space. It's hurtling towards the Milky Way at like 68 miles per second, or somewhere around that range. So, 4.5 billion years away from collision with the Milky Way. But it's really exciting to be able to see that it is actually moving through space towards us. And it is just so beautiful. Great question.
Okay, I don't see anything in the chat, so we'll go ahead and wrap it up there for today. Thank you all for joining us. Maria, thank you so much for joining us and helping us discover more about our world, our galaxy in this case, our universe really. So please join us next week. Now, special time for next week for Lunch Break Science will not be on Wednesday. It will be on Monday the 21st at noon, because we are going to have with us ophthalmologist Dr. Evan Silverstein. With all the distance learning and everything and all the screen time that we're getting in the pandemic world, you might be wondering what it's doing to your eyesight. So we have an ophthalmologist here who is actually going to discuss that with us. So he'll be presenting virtual learning and your eyesight. Again, that's going to be noon on December 21st. Each talk is free to attend and is open to the first 300 registrants. You can register at smv.org. Thank you again for joining us today. Until next week, stay safe and stay curious.